Today's lesson is on similarity of figures. Now, how can we tell whether two figures of different sizes have the same shape? One of these logos has a distinctly different shape from the other two. How can we determine whether the two logos that look actually alike have the same shape? So I'm going to give you the dimensions. So one is 2.3 by 1.3 centimeters high. The other one is 4.6 centimeters wide by 1.3 centimeters high. And the last one is 4.6 centimeters wide by 2.6 centimeters high. So what we're going to do is compare A and C because they look the same shape. So we're going to take the height of 1.3, divided by the height of the C, which is 2.6. And then that's going to compare the height of both. So the scale factor is 1/2, or the ratio of the dimensions are 1/2. We're going to compare the widths with 2.3 over 4.6, which is also 1/2. So if you calculate the ratios, then you will determine, and they are the same, then you actually can prove that these two shapes are similar. We can do that with some rectangles too. So I put in the dimensions. This should be a 3. Okay, so you would take side 2.2 of B and compare it to side 3.3 of A and figure out the decimal ratio. You're going to take 2.2 of B and compare it to the other side, 1.6 of B. And they don't have the same scale factor. 0.6 is not the same as 1.375, so these are not similar. If I do the same with A and C, I actually find out that 2.6 or 1.6 to 2.6 and 3.3 to 5.2, I get a ratio in decimal form at 1.625 for both, so that makes those two shapes similar. Similar in math means the same shape. If two rectangles are similar, the ratio of the length of any two sides of one rectangle is equal to the ratio of the lengths of the corresponding side. So AB corresponds to A prime B prime. BC corresponds to B prime C prime. Okay, so those two sides are in proportion. We can extend the concept of similarities to all polygons. If two polygons are similar, then the ratio of the lengths of any two sides of one polygon is equal to the ratio of the lengths of the corresponding sides of the other polygon. Remember, if they are similar, though, the corresponding sides have to be in proportion, and the corresponding angles have to be congruent. So we have to check two parts, not just one, to determine that they are similar. Paul is a francophone cabinet maker who lives in Calgary. He creates a bank of cabinets that will be 10 feet long by 3 feet high. He wants to create a scale diagram on graph paper with measurements that are 1/12 of the real life measures. What are the size of the cabinets beyond the diagram? Well, we're going to put it on graph paper, so we're not working in feet. So we're going to change 3 feet into inches, so 36 inches times 1/12, because we want it to be 1/12 the size, says in the question. And so 36 times 1/12 equals 3 inches long. So your diagram is going to be 3 inches long, well, or high, feet high, inches high. So this is the height, and this is the length of the diagram. Okay, 10 feet into inches is 120 inches times 1/12 is 10 inches long. Similar, use the correct scale. So how do you know they're similar? You use the correct scale for all measurements. So you actually have to be careful to measure correctly. You're going to use a ruler and measure 3 inches and 10 inches to make sure that they are similar. The other way to do this question, so this is another option, is scale over original. So your scale factor is always the scale over original. So we're going to put our scale factor here, 1/12. Our scale, we don't know. That's what we're looking for. The original is 36. So when we cross multiply, I have 1 times 36, and I have 12 times x. And so we solve to find out x is 3 inches, and we can do it on the other side as well. Make sure that the scale diagram is always on the top and the original is always on the bottom. Cross multiply to find out the other answer is 10 inches. So you get the same answer, just whichever way makes more sense to you. When two figures are similar, one figure has dimensions, length, and width that are in proportion to the other figure. A set of toolboxes can be placed inside each other to save space and therefore shipping costs. When shipping the toolboxes to retailers, it's easier if one fits inside the other. These toolboxes may have dimensions that are proportional. Each box has the length and width in the same proportional ratio than the next larger size. If the largest toolbox has a length of 600 millimeters and a width of 300 millimeters, and each smaller box is 4/5 the size of the box before it, what would be the length and the width of the second and the third toolboxes? So we start off with our scale factor on one side, 4/5 equals the scale diagram we don't know, but we know the original is 600. So then we cross multiply to solve. Okay, and x is going to be 488 millimeters. Okay. The width, same scale factor, 4/5 times x over, or equals x over 300 this time. And we cross multiply, we get x equals 240 millimeters. Now, when we do the next box, we actually have to use the dimensions from the second box, not the first one. So again, the same scale factor, but we want to make the second box smaller. So we get 480 this time. Okay, so we're going to take the second box and make the third box, which goes inside. It's going to be smaller, and it's 384 millimeters. And 4/5 equals x, because we don't know the scale size, but we know it's 240. So x equals 192 millimeters. Similar figures have to have the same shape, but don't have to be the same size. So photos are a very good example of similar figures. You could have a photo that's bigger or a photo that is smaller, and they are called similar figures. So here's a diagram of two triangles, and we want to determine the corresponding sides and the corresponding angles. That means that they hold the same position. So angle A is at the top of your triangle. Angle P is also at the top of the triangle. They are both corresponding, okay, and they also are congruent. That means that they are the same size. Angle C and angle S are also congruent and corresponding, so they need to be in the same position. And B and Q are also in the same position and corresponding, and they're 80 degrees. Okay? Now, AB, side AB, is going to correspond to side PQ. Okay? Side BC is going to correspond to side QS. Okay? And side AC is going to correspond to side SP. Now, they are all equal because the ratios are equal. If I took the length of AB, divided it by the length of PQ, that would equal the scale factor, which would equal PBC divided by QS. Now, the one thing that's very important is the order in which you write the corresponding angles. The little curly sign like this means corresponding or similar. So triangle ABC is similar to PQS. Angle A corresponds to angle P, which is shown here. And so they would be first when you write it to show that they're corresponding. Q and B are corresponding, so they would be next. And C and S are corresponding. Now, we could have started somewhere else. We could have said S or C corresponds to S. A corresponds to P, and B corresponds to Q. Okay? You also have to be careful because AB, side AB, corresponds to side PQ. So side AB still needs to correspond to side PQ. Angles that are equal or the same size, remember size, they are called congruent. So make sure you remember that they are congruent. Debbie works for a magazine and is adjusting the dimensions of some images to fit into an article. She is not certain that she has changed the length and width by the same amount and wants to find out if she has used the same ratio for each direction. The original photo is 4:2 and the changed image is 6:3. What is the ratio of the length? Okay, so we're going to look at the length is the scale, which is the new one, is 3, by the original is 2. And so that would be written this way, or it could be written as with a colon. The second, the width, would be corresponding, so the scale goes on top is 6, the original is 4, and that would be 3/2. You always reduce, or it could be written as 3:2 that way. The ratios are the same, so the two photographs are similar. A family built a home in Regina and designed a backyard garden in the shape of a trapezoid. Over the years, they loved the design they had created, and when they moved to a larger property, they decided to use the same shape for their new backyard garden. They mapped what they did for the first garden and then created a map of the trapezoid that would fit the new space. Okay, so we're going to determine if the two shapes are similar. So we need to find corresponding sides and determine if the ratios are the same, and also look to see if the angles are equal. So this is 71. So this one would also need to be 71 because they're corresponding. This angle is 71, and this angle needs to be 71. This bottom angle is 109, so the corresponding angle would be 109. This bottom angle is 109, so this corresponding angle needs to be 109. A definition of a trapezoid means that the base angles are equal and the top angles are equal. So far, we do have a similar shape, but now we got to check the sides. So side AB corresponds to side EF. Now this is the scale because it's the new one, and this is the original. So it's always a good idea to label your diagrams so that you know which ones you're comparing. So I am comparing EH to AD, and it's 15 to 10. When I divide that out, I get 1.5. I'm going to compare HG to DC. It's 10.8 to 7.2. So I'm just comparing these two sides here. Divide it out, I get 1.5. EF is corresponding to AB, 20.4 divided by 13.6, and again the ratio is 1.5. FG corresponds to BC, so 15 over 10 equals 1.5. So our sides are all the same proportion, so yes, these two are similar. If I was going to write down the two shapes, I would say that A, B, C, D is similar to E, F, G, H. Okay, double check to make sure you did it right. A and E, angles A and E, are corresponding, and AB corresponds to side EF, and CD corresponds to GH. So you've written it correctly. A tissue company creates tissues for their dispensers in the shape of rectangles. Each tissue has a length of 9 centimeters and the width of 10 centimeters. The manufacturer wants to increase the length of their tissues by a factor of 1.7, but keep the same width so they fit in the dispensers. draw a sketch of the original tissue box and the new dimension, so I did that. And one is 10 by 9, and the other one is 10 by, and we're changing the length by a scale factor of 1.7, so 9 times was 9, we increased it by 1.7, so the new length is 15.3. So, are these similar figures? Well, the corresponding lengths and widths have not been increased by the same amount. The 10 stayed the same, but the length has been changed by a scale of 1.7. So they are not similar figures. All right, I'd like you to practice your new skills with Build Your Skills and Practice Your Skills in the workbook, page 262.